Hi, Josephine. My name's Ross. I saw your problem and it's really interesting, so I hope I can help you out with it. There's a lot going on here, but I want to start with the very end here where it says that we're trying to prove that two triangles are similar. We got to do a lot to make that happen, but at the very core, that's what we want to do. So first, just some quick review about how that works. To prove that two triangles are similar, we can use these postulates, these kind of rules. There are a handful that you can use. One, for example, is the angle side angle postulate that says if two angles in triangles match and one side matches, that you can say those triangles are similar. You also have one called the angle postulate, or AAA. I bet you can figure out what that means. If all three angles match in two triangles, then you can say they're similar. And that's actually the one that we're going to use today because it's one of the easier ones, and it's going to be the, easier to figure out in this particular problem as well. One more thing, another trick that's going to help us is actually something else that we know about triangles, and that's that the three angles in a triangle add up to 180 degrees. So let's consider an example. Let's say that in this one we have 30 degrees. Let's say this one is 100. Okay, and then let's go ahead and say in this other triangle as well. Let's say this one's 30 and this one's 100. Okay, well obviously we have two pairs of matching angles. And yeah, the triangles are different sizes, but that doesn't have any impact on the angles, so this is possible. So what would the third angle be in each triangle? Well, we should know that all three interior angles of a triangle add up to 180. So to find this missing third angle here, we could do 180 minus 100 minus 30, or we could add those two up and then subtract. Regardless, you'd end up with 50. And so what about this third one over here? Well, without doing any math, hopefully you realize if the third one here was 50, the third one here will be 50. So why that's important is because that tells us that, in fact, if we know two of the angles match in two triangles, then we don't even need to know the third one. If two angles match, we can automatically say that those triangles are similar. And so that's what we're going to try and do today. So all of that is a setup. We want to try and find two angles in these triangles, but there are no triangles, right? It talks about triangles, and where are they? So I've got part of a picture set up here. I've got my circle drawn, and it starts to talk about these arcs, which is just a piece of a circle. It's a curve on a circle. It says that we want APB to be one of our arcs. So that's this one here, APB. And P can be anywhere. I put it where it is, but it doesn't have to be. And ACB, where C is the midpoint. And so just to make that clear, and this will be helpful later too, I'm going to put two little marks here. I'm going to put a mark here and a mark here, and that's just me telling myself that I know AC, this little piece, and CB have to be equal. If C is in the midpoint, then those two pieces between A and B have to be the same. Okay, one other thing actually, just in case, as I was trying this one, I noticed, and they should have said this in the problem, C and P actually cannot be on the same side of the circle. So if you're having trouble, that may be why. They do need to be on opposite sides on different arcs. All right, so let's go ahead and continue here. So it says if chord AB and chord CP cut, or if they intersect. So remember that a chord, that's just a fancy word for a segment, a little piece of a line that connects 2 points on a circle. So chord AB would be right there. Chord CP would be right there. And it says that they intersect here at E. Okay, so we've got those two chords intersecting, but I still don't see any triangles, right? I don't see any perfect triangles. So here's what's going to have to happen. They say something about triangle APC. So what I'm going to do to create that is I'm going to connect all three of those letters, and I'm going to do that here in green. So to make that, I'm going to go from A to P, from P to C, which you'll notice is actually, I'm just tracing over one of those chords, and then from C to A. So that's our first triangle there, and you may notice that looks oddly similar to this triangle I have over here. That's on purpose. We'll use that here in a minute. And then the second triangle that I'm going to use is EAC. So this one I'm going to trace in purple. And EAC, again, I'm going to start at E, trace to A. That traces over another little piece we had already drawn. From A to C. And I'm going to try and move that over a little so we can see that it's both purple and green. And then from C to E. And again, I'm going to try and show that's purple and green. So two of those are part of both triangles, the bigger and the smaller one. All right, so we have the triangles, and you'll notice that purple one I also have redrawn over here to the right. So we have the triangles. We know that we need to match up two of the angles, but how do we do that? There's no numbers in this problem. It's not like a minute ago where I could say this one's 30, this one's 30. So what do I do? Well, did you notice that I haven't mentioned these two little blue marks in a minute? That's where these are going to come in. We're going to use the relationship between these arcs and some of the angles in the picture. Really quickly, I want you to come over here down to this circle that's down at the bottom right, and I want to remind you of something that's called an inscribed angle. An inscribed angle is something like this one, where we have two segments connecting points on a circle, and you'll notice that the vertex, the kind of corner, is on the circle. Ooh, that's a crappy point, but there it is. And the other 2 points are also on the circle. So it's an angle that connects just 3 points on a circle. There's a special relationship here that says that this angle has the same degrees as this, or excuse me, half of the degrees as this arc. That's not so much important as it is that there is a relationship between this angle and this arc. If you know one, you can find the other. Super important for this problem. So let's come back over. Why is that important here? Well, if you look here at this, this first arc that I had marked in blue, this arc is being made by this inscribed angle APC. So this angle has half the degrees of that arc. So that's this one right here. I'm going to trace that in this orange color. So that's this angle. I can also see back over here to this blue arc, this one I marked. This is being made by this other inscribed angle. I don't know how many degrees it is, but like I said over here a second ago, if you know the arc, you can find the angle. So if we know both of those arcs have the same length, that means that these two angles also have to be the same. So angle CAB here and angle APE, or angle APC, have to match. This is going to get pretty messy. So that's why I actually redrew the triangles over here. I'm going to remark those in separate triangles so we can kind of see them separately instead of all in one picture. So angle APE, that would be up here. So all I'm doing is I'm taking this angle and redrawing it just in a separate spot. And then I'll do the same thing here. The orange angle is right there. So far we have one angle that we know matches. And what I said at the beginning was if we can find two, that's all we need. So I know that one pair of angles matches. Don't know how big they are, 10 degrees, 80 degrees, doesn't matter. I know that they match. So how can I prove that some of the others match? This, I think, is going to be the hardest part of the video. So what I'm going to do is, again, I don't know how many degrees they are, so I'm going to give these angles a name. I'm going to call these angles theta, which is just a stand-in for an angle. So theta looks like a little zero with a line through it. And I'm going to remind you again of a relationship that we know between triangles. Number one, they all have to add up to 180 degrees, the three angles inside a triangle. And another thing we know is that two angles that combine to make a straight line are supplementary, which means they also add up to 180. That would help, except I don't know what any of these angles are. I don't know the degrees. But it might help if I start to draw some comparisons between the angles that are adjacent. So I'm also going to call this angle here, I'm going to call this alpha, which is a Greek letter, kind of like A, looks like a little fish almost. And I'm going to use that to find some additional relationships. One that I can say is that this pair of angles here, okay, so this angle where we have alpha and where we have the one right next to it, those are supplementary, so they have to add up to 180. I don't know what alpha is, so I can't subtract, a number from 180, but I can say for sure that this angle is 180 minus alpha. I don't know what number that is, but if I took alpha and subtracted it from 180, I would end up with that angle. So now I've got some more information. And why am I throwing all these letters around? It's because it's allowing me to find more information about the other angles involved. I may still not know what numbers they are, but I at least have some way to talk about them. And now let's look at this next piece of the puzzle. If I'm looking at this smaller triangle here, I have two of the angles, and I know again that all three angles add up to 180. So let's think about that. If I add these two up, that'd be theta plus 180 minus alpha. I don't know what the two variables are, but if I subtract that from 180, if I subtract all of that from 180, I should end up with my last angle, which is this one up in the corner. Okay, so I have 180 minus, if I distribute this negative, I'll have 180 minus theta minus 180 plus alpha. So that'll give me 180 minus 180 will be 0. I'm going to put the positive alpha in front and then minus theta. So that is going to be this angle up here, EAP. So EAP is alpha minus theta. Now we've got one more thing to do. Notice that part of our green triangle here, we now have both pieces of that puzzle. This yellow angle is the combination of these two smaller angles. One of them is this alpha minus theta. The other is just theta. If we add those together, what happens? The thetas cancel and we're left with alpha. So this yellow angle up here is alpha. Okay, well, who cares? Well, just a few minutes ago, we also said that angle AEC, which is right here, is also alpha. So I guess I should color that in yellow because they are the same. So all of that work got us to the point where we have two angles in each triangle that match. And so based on what we know about triangles, that means these other two angles automatically match and the two triangles are similar. So that is a very difficult problem. It has a lot involved in it. You got to know about circles. You got to know about midpoints, about triangles, about triangle postulates, all this stuff. But if you can put all that together, you can positively prove that those two triangles are similar. I hope that that's helpful. Please feel free to leave me a comment or a question, and I can help if you need some additional assistance. Until then, see you next time.